In Lecture 5 we'll talk about exponential growth. We have many quantities in nature grow or decay at a rate proportional to their size. For example, a colony of bacteria might double every hour, and we could express this mathematically as saying dy dt equals 2 times y, where y is the size of the population and t is measured in units of hours. Any quantity y that grows or decays at a rate proportional to its size is going to fit an equation like this: dy dt equals k times y. And this is a very special example of something called a differential equation. And that's an equation which gives a relationship between a function and one or more of its derivatives. And if the k is positive, we call it the law of natural growth. And if the k is negative, then we call it the law of natural decay. And the solution to the differential equation is any function y which satisfies the equation. So for example here, a solution to this differential equation is any function y whose derivative is k times the value of the function itself for any given value of t. It's not very difficult to see that y equals e to the kt is a solution to this equation. Why is that? Because if I differentiate e to the kt, I get k times e to the kt, which is k times the function itself. So therefore, this function satisfies or is a particular solution to this differential equation. Now, it's not the only one. As with antiderivatives in Calculus 1, there's a family of solutions to this equation. We can see that if I pick any constant c and take the function y equals c times e to the kt, that this function also fits the differential equation. If I differentiate this function, then I get c times k e to the kt, which is k times the value of the function itself. So therefore, any function that looks like this is also a solution to this differential equation. Later, when we study differential equations, we'll show that this exhausts the possibilities for solutions to this differential equation. This is the entire family of solutions to this differential equation. And I can say a little more about that constant c. If I pop in t equals 0 into this equation, I get y of 0 equals c times e to the k0, which is c times 1, because e to the 0 is 1. So we find that c is actually the value of the function at 0. So the only solutions to this differential equation look like this. They're y of t equals the value of the function at 0 times e to the kt. And the function itself is completely determined by the value of the function at 0, and this makes sense if you think about it. If you give the value of the function at 0 and you have a formula for how the function is growing, then the path of that function is completely determined by this formula, and so the function itself is uniquely determined by its value at 0. This is called the initial value of the function. And here we show a picture of 3 different solutions to the differential equation dy dt equals 2t. Here are 3 of the possibilities. We picked 3 different values for y of 0, and these are the 3 solutions which run through those particular values 0, y of 0, or that particular initial point on the curve. There are many more solutions. We can pick any value for y of 0, and there's a unique solution running through the point 0, y of 0, or whose graph runs through the point 0, y of 0. So we get a solution for any given initial value for this equation. Population growth is well modeled by exponential growth up to a point. And I say up to a point because there are certain limitations on population growth, and the model breaks down when the population gets overcrowded and resources become scarce. But for populations without many restrictions, they will grow exponentially. And dp dt, the population changes at a rate proportional to its size. So we get dp dt equals k times p. That k will vary from population to population. And then the size of the population p of t is a solution to that equation. And that's the initial size of the population p of 0 times t equals 0 times e to the kt. And the relative growth rate is k. It's the change in population growth over the size of the population, and that's a constant, and that is peculiar to the population. In class, we'll look at examples like this, where we're given an initial size for the population, we're given the rate of growth, the value of k, and we want to determine or project what the size of the population will be after t years. So we want to find a value for p of t for a given t. And also, there are some twists on these problems. You might have data that looks like the size of the population in year, say, 2000, and then the size of the population 10 years later, and from that data you can extract the value of k, assuming exponential growth, and you're given p0, and therefore you can find the population size, or the function that gives the population size at any given time, and you can use that to project the size of the population in the future. Other places where exponential growth is very useful is radioactive decay, and radioactive substances decay at a rate proportional to their mass. So they follow this equation. The derivative in the mass with respect to time is k times the mass, where the k varies depending on what substance we're talking about. And therefore, the mass of the substance at time t is a solution to that equation. So the mass of the substance at time t is the initial mass times e to the kt. So once you know what the k is and the initial mass is, you can figure out the mass of the substance at time t. Another number that's often quoted for radioactive substances is the half-life of the substance, and that's the amount of time it takes for the substance to be halved. And given the half-life of, say, something like carbon-14, here it is, it's 5,730 years, you know that if I have any initial quantity of that, then it takes 5,730 years for that quantity to reduce to half its size. And this can be used for a process called carbon dating, which is often used to figure out the age of artifacts. And one can do that by estimating the mass of carbon-14 in the object when it was made. And then, since one knows the half-life, one can work backwards to figure out the value of k, and this tells us that the amount of carbon-14 in the object at time t after t years is m of t equals m0 times e to the kt. And we can then measure how much carbon-14 is in the object at present and compare that to the amount that was there initially, and that allows us to figure out this value of t. So in class we look at examples that look like this. We might be given the percentage of the original carbon-14 in a bowl is estimated to be 40% of the carbon-14 that was there originally, and then from that data you can just estimate the age of the bowl using this half-life. Now there are slight variations in the decay of carbon-14 depending on the environment, and this method is not entirely foolproof. We can also use exponential growth for interest, which is compounded continuously. So the amount in an account at time t is A of t, and this varies according to the rate of interest. And so if the rate of interest is r by 100% per year, then the amount is changing at a rate, the derivative is r times A of t. Hopefully it's increasing at an amount r times A of t, and this obviously is a differential equation, and the solution is A of t, the amount in the account at time t, is going to be the initial amount times e to the rt. So after t years, the initial amount A naught will grow to A naught times e to the rt. And again, we'll look at some problems. If I invest an initial amount of $1,000 for 5 years at a given interest rate, how much will be in the account after 5 years, and how long before the account will grow to $2,000, say. Interest doesn't have to be compounded continuously. It might be compounded quarterly or monthly. And this all fits in with the continuous compoundation in this manner. So we have a bunch of formulas depending on the value of r, depending on the number of times the interest rate is compounded per annum, and depending on the initial amount. So if I put $0 into an account for 1 year with an interest rate of r by 100% per year, then after 1 year I get r times A0 added to my initial principal A0, so I have A0 times 1 plus r dollars in my account. I start out in the second year with that amount in my account, and then at the end of the second year I have that amount multiplied by 1 plus r in the account, and at the end of t years I end up with the initial amount times 1 plus r to the power of t in the account. If the interest is calculated monthly, then at the end of 1 month, because the interest rate is quoted as the interest rate per year, I just get 1 plus r over 12 times A0 in my account at the end of 1 month. At the end of 2 months, I have A0 times 1 plus r over 12 times 1 plus r over 12 again in the account. And then at the end of 1 year, I have A0, my initial amount, times 1 plus the interest rate over 12 to the power of $12 in my account. After t years, I have that initial amount times 1 plus r over 12 to the power of 12t in my account. And now, interest is compounded continuously. That would mean that interest is calculated n times per year, and that n is very, 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 very large. So we let n go to infinity to find our formula for interest which is compounded continuously, and that would be the interest, if interest is compounded continuously, the amount in the account after t years is the limit as n goes to infinity, the number of calculations per annum goes to infinity, of A0, the initial amount, times 1 plus r over n to the power of nt, where t is the number of years and r is the rate of interest. And so, of course, that limit, according to our exploration of those limits, is a0 times e to the rt. So we get the same formula if we approach continuously compounded interest from this limiting point of view. So we'll do some examples in class where the interest is not compounded continuously, but it's compounded perhaps quarterly, and we won't always just think about investing money, we'll also think a little about borrowing money.